This encryption was built to survive quantum computers. It went through years of intense scrutiny. Mathematicians and cryptographers picked at it from every angle, and then a new technique came along and cracked it wide open, not with a quantum computer, but with pure math. The algorithm is called Hawk. It was one of the finalists in a long-running competition to find encryption standards that can hold up in a world where quantum computers eventually exist. Today's encryption relies on math problems that are easy to set up but brutally hard to reverse. Quantum computers threaten to make those problems much easier to solve, so researchers have been racing to find new algorithms built on different math, problems that even quantum machines would struggle with. Hawk was a serious contender. It's a digital signature scheme, which means it's used to prove that a message or piece of data is authentic. Think of it like a cryptographic seal of approval. When you download software, or a server proves its identity to your browser, or a document needs to be verified, that's where digital signatures come in. Hawk's job was to do all of that in a way that future quantum computers couldn't forge. The math underneath Hawk is based on something called lattices. A lattice is basically a grid of points in very high-dimensional space. The hard problem at the core of lattice cryptography is finding the shortest path between points in that grid. Even roughly solving it in high dimensions is considered extremely difficult. That's why lattice-based algorithms became one of the most popular directions for post-quantum cryptography. The math seemed solid, but here's where Mythos comes in. Mythos isn't a quantum attack. It's a classical cryptanalysis technique, meaning it runs on ordinary computers. What makes it different is how it looks at the problem. Most cryptanalysis tries to attack the hard math problem directly. Mythos takes a different approach. It looks at what leaks out during the signature generation process itself. When Hawk generates a digital signature, it has to do internal calculations. Those calculations involve secret values, the private key material that makes the signature unique and secure. Mythos is designed to observe many signatures over time and then work backwards. Each individual signature doesn't give much away, but if you collect enough of them, patterns start to emerge. The secret values leave faint statistical fingerprints across all those outputs. Mythos is essentially a lattice reduction attack combined with careful statistical analysis. It gathers signatures, extracts those faint signals, and then uses that information to dramatically reduce the size of the search space. Instead of trying to find the private key in an astronomically large haystack, Mythos keeps shrinking the haystack until the key becomes findable. And with Hawk, it turns out the haystack shrinks far too much. The reason this is so striking is that Hawk passed years of formal evaluation. The post-quantum standardization process is rigorous. Cryptographers worldwide submitted attacks. Hawk held up. The people running the evaluation are genuinely excellent at this. And yet Mythos found something that the entire process missed. That's not a knock on the evaluators. It's actually a reminder of something fundamental about cryptography. You don't know what you don't know. A new analytical lens can reveal weaknesses that older techniques were simply blind to. Mythos represents a new lens, and when that lens was pointed at Hawk, a fatal flaw appeared. The technical term for what Mythos exploits is a secret key recovery attack. Given enough signatures produced by the same private key, Mythos can recover that key entirely. Once you have the private key, the whole system collapses. You can forge signatures. You can impersonate any identity that used Hawk. Everything it was supposed to protect becomes compromised. The number of signatures needed to pull this off matters a lot. If you need billions of signatures from the same key, it's less practical. But the researchers behind Mythos showed the attack works within a realistic range. That's what moves it from a theoretical concern to a real disqualifier. So Hawk is effectively out of the running. That's actually how the process is supposed to work. Better to find this now than after governments and companies have deployed it everywhere. The whole point of the long evaluation period is to stress test these algorithms before they become critical infrastructure. The broader lesson here is about diversity in cryptanalysis methods. For a long time, the field had well-established playbooks for how you attack a cryptographic algorithm. Mythos represents a new page in that playbook. Its existence raises a natural question. Are there other candidates in the post-quantum lineup that might have similar blind spots, weaknesses that current techniques just aren't designed to see? That's not a reason to panic. The standardization process continues, and the algorithms that have already been selected went through enormous scrutiny. But it does suggest that the work of evaluating post-quantum cryptography isn't really finished. It's ongoing. New techniques like Mythos will keep probing. That's exactly what should happen. For now, Hawk joins a list of algorithms that looked promising and didn't make it through, and Mythos earns its place as a meaningful new tool in the cryptanalysts' kit. The goal was always to find the strongest possible foundation for encryption before quantum computers make the stakes even higher. This is that process working, painful as it looks from the outside.